Hello everyone. Today we will going to see the topic electrochemistry in detail, and this is part 2. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is our index slides and these are the major topics which we will going to study, which we will going to cover today one by one, in which it includes salt bridge, EMF of a galvanic cell, electrode potential and standard electrode potential, electrochemical series, Nernst equation and its applications, relationship between cell potential and Gibbs energy change, batteries, fuel cells or corrosion and its prevention. Right? So let's start with our first topic, salt bridge. It is a U-shaped tube containing a gel permeated with a solution of an inert electrolyte such as NH4NO3 ammonium nitrate. The ions of inert electrolyte do not react with the other ions in the solution and they are not oxidized or reduced at the electrodes. The salt bridge is necessary to complete the electrical circuit and to maintain electrical neutrality in both the compartments by flow of ions. Basically, salt bridge, as you can see in this diagram here, that this is a salt bridge. This silvery thing, U-shaped tube, is a salt bridge, and in this salt bridge, it contained a gel, okay, through which the flow of ions happened from one solution to the other solution, and it also contains some inert electrolytes which do not react with either of the solutions or do not oxidized or reduced at the electrodes present in the circuit, right? And salt bridge is necessary because it completes the electrical circuit to pass the current from one electrode to the another. Okay, so this is the cell, or this is the diagram for the salt bridge, and this is the reaction happening in this diagram, that is zinc plus copper 2 positive, giving us zinc 2 positive plus copper. Zinc is here, which is on anode, and copper is here on cathode. Okay, current is flowing in this direction and electron is flowing in this direction. Sorry, current is flowing in this direction, right, as the arrow says. And this is anode, this is cathode, this is salt bridge. Okay, and this is the solution containing zinc salt, and this is the solution containing salt of copper. Okay, now let's see about the difference between electrolytic and electrochemical cells. So the main points of difference between these two cells are: first one, the device in which electrolysis, chemical reaction involving oxidation and reduction. Okay, electrolysis is a process. Electrolysis is a process in which a chemical reaction is happening, in which oxidation is also occurring and reduction is also happening simultaneously. So a device in which the electrolysis is carried out by using electricity, or in which conversion of electrical energy into chemical energy is done, is called electrolytic cell. Okay, while galvanic or voltaic cell is a device in which redox reaction is used to convert chemical energy to the electrical energy. So opposite processes are happening in these two cells, that is electrolytic and galvanic or voltaic cells. In the electrolytic cells, energy or electrical energy is converting into chemical energy, and in the galvanic or voltaic cell, chemical energy is converting into electrical energy. Now in electrolytic cell, anode is positive electrode while cathode is negative electrode. On the other hand, in galvanic cell, anode is negative electrode and cathode is positive electrode. So in both the cells, anode is always the site of oxidation and cathode is always the site of site of reduction. Okay, this is same that that on anode oxidation will happen, on the cathode reduction will happen, but in the electrolytic cell the negative electrode is cathode, positive electrode is anode, while on the other hand in the galvanic cell the negative electrode is negative electrode is anode and positive electrode is cathode. Next point, that in electrolytic cell ions are discharged at both the electrodes, while in galvanic cell ions are discharged only at cathode. Okay, so in the electrolytic cell ions discharged at both electrodes, that means on the anode and on the cathode both, but in the galvanic cell ions discharged only at cathode. Okay, in electrolytic cell both the electrodes are fitted in the same compartment, while in the galvanic cell both the electrodes are fitted into different compartments. So this is galvanic cell, and in the galvanic cell both electrodes fitted in different compartments. In the electrolytic cell both electrodes are fitting in same compartment. You can see the diagram also. Here it is electrolytic cell, the EMF is applied to the cell. Here it is positive one is anode, negative one is cathode, and this is the circuit, and electrons is flowing from this to this direction, and you can see that the both electrodes are fitted in the same compartment, right? There is no separation. While in the voltaic or galvanic cell negative electrode is anode, positive electrode is cathode, and the electron is flowing in this direction, and there is a partition of compartments between the electrodes, right? So both the electrodes are in different compartments. These are the main major differences between the electrolytic or galvanic cell. Okay, now let's talk about the representation of a cell. How can we represent a cell? So consider the Daniell cell with the following cell reaction. Zinc plus U2 positive will give us zinc positive plus U. Okay. Now the complete cell diagram may be represented as follows for this cell. That is zinc in solid. This line is phase boundary. Okay, this is known as phase boundary. So in these two, zinc and zinc 2 positive aqueous, the phase boundary is present. Double line is showing for the salt bridge representation, and it is giving us copper 2 positive and phase boundary copper solid. Okay, and this one on the left hand side is anode half cell, this one on the right hand side is cathode half cell, and the flow of electron is in this direction, in this way. Okay, so if you want to write the cell, or the structure of cell, the cell diagram, you can write it in this way, other than drawing the compartment or the electrodes and the circuit completely. You can write the diagram of a cell through the cell reaction through this, with the help of this diagram also. Okay, this cell diagram, in which cell bridge is also representing, and phase boundary is also present, cathode half cell is also present, anode half cell is also present. Okay, so you can write the cell diagram with the help of cell reaction, with the help of cell reaction, like this. Okay, in writing a cell diagram, following points are considered. We divide the cell into two half cells first of all. Okay, the anode one and the cathode one. Okay, and the reaction is oxidation takes place on the anode, so zinc giving us zinc 2 positive plus 2 electron, losing of electrons. On the cathode, reduction takes place, so gaining of electrons, copper 2 positive plus 2 electron giving us copper solid. So first of all we write the reactions, two half cell reactions. Okay, now let's see the terminal. So anode 1 is negative 1, cathode 1 is positive 1. Let's see the side. So anode is present at left hand side, cathode will be present at right hand side. And how can we write, like how will be the diagram of this cell for this half cell reaction happening on the anode? It will be zinc solid, line zinc 2 positive aqueous. Okay, so this is the representation, this is the diagram. On the cathode, this is the diagram for representation of reduction, that is copper 2 positive aqueous, line copper solid. Okay, so while writing the cell diagram like this, we have to follow some rules. We have to consider some points, and these are given in this table. That the first of all, you should have to know the half cell reactions of two oxidation reduction happening on the anode and cathode. You should have to know the terminal of anode and cathode. You should have to know the side of anode and cathode, and then you can write the diagram of the every half cells for the anode and the cathode. Okay, so let's move to the topic EMF of a galvanic cell. In electrochemical cell, the electrodes in different half cells have different reduction potential. This difference in electrode potential of electrodes, due to which electrons flow from anode to cathode, is called electromotive force or EMF, or cell potential of a cell. Okay, so the difference in the electrode potential of electrodes, due to which the electron flow from anode to cathode, this difference is known as electromotive force or cell potential of a cell. This is driving force for all the cell reactions. This is the driving force because due to the presence of electromotive force in a cell, so the electrons movement or the flow of electrons is happening from one electrode to another. That's why the cell reaction is happening. So electromotive force or cell potential of a cell is a driving force for all the cell reactions. Okay, now electrode potential and standard electron potential. So in the potential also we have two terms, electrode potential and second one is standard electrode potential. So let's see, if we connect two different electrodes, electrons will flow from the electrode of higher negative electric charge density to the lower negative electric charge density. Okay, so if we have different two electrodes, we connect them, the electron flow will start to happen, and it will happen in the direction, it will flow in the direction of from higher negative electric charge density to lower electric charge density. A property closely related to the density of negative electric charge is called electrode potential. Potential difference between the metal and the metal ion in which electrode is dipped is called electrode potential, denoted as capital E. In the standard state, when pressure is 1 atmosphere, latest IUPAC correction is that you should use 1 bar. So temperature is 9 to 98 Kelvin, standard conditions, and concentration is 1 molar. The electrode potential is called standard electrode potential and denoted by E0. According to international convention, if the standard electron potential of half cell is 0.34 volt, it means it is the standard reduction potential E0 Mn positive M of half cell Mn positive line M, with a half cell reaction of Mn positive plus N electrons, giving us M metal atom in solid. And if E0 of oxidation is equals to X volt, then E0 of reduction, that is standard electrode potential of reduction, is equals to minus X volt. Okay, so these are some basics, and now let's study more that E0 of a cell or E of cell is potential difference between two half cells. Since the potential difference is driving force for electrons to move them, right, it is also called electromotive force or EMF of the cell, or the cell potential or cell voltage. Okay, the SI unit of cell potential is volt, and the potential of a galvanic cell is defined as positive quantity. E0 cell will be equal to E0 of oxidation plus E0 of reduction, or you can say E of cell is equals to E of oxidation plus E of reduction. E is potential difference, right, or electromotive force. And you can represent it in standard form where all the conditions are standard, and you can represent it in normal form. Standard hydrogen electrode SHE, used as a reference electrode, its reduction potential is taken as 0. It is represented as this much: platinum, H2 1 atmosphere at 1 atmosphere, phase boundary H positive in 1 molar solution, or H positive in 1 molar solution, phase boundary H2 at 1 atmosphere, platinum. So you can represent it, the standard hydrogen electrode, you can represent by any of the pattern, depending upon whether it acts as anode or cathode respectively. Okay, so if it is acting as an anode, the standard hydrogen electrode, we are talking about the electrode here. Okay, so standard hydrogen electrode, if it is acting as an anode in the circuit, then we use this representation, and if it is acting as a cathode, then we use this representation. Okay, the difference between potential required for the evolution of gas and the standard electron potential of that gas is called overpotential or overvoltage. Okay, this is also important. Now let's see the electrochemical series. There is a list, or you can say the arrangement of metals in decreasing order of tendency to lose electrons is called electrochemical series. So you can see in this diagram also that elements are arranged, metals are arranged, and this is the increasing tendency for reduction. Okay, and if you go from bottom to top, it is the increasing strength of reducing agent. So the decreasing tendency of lose electrons, and the series of the metals is known as electrochemical series. So basically we arrange the metals according to their tendency of losing the electrons. It is a series in which the elements are arranged on the basis of values of their standard reduction potential at 25 degrees Celsius. Or you can also say that electrochemical series is a series in which elements are arranged on the basis of the values of their standard reduction potential at 25 degrees Celsius. So at 25 degrees Celsius, what is the standard reduction potential? It is showing, they are showing what will be the value. So on the basis of that value, we have arranged the elements in order, and that series is known as electrochemical series, represented here. You can see lithium is on the topmost and the fluorine is on the bottommost. Okay. Now, Nernst equation and its applications. So what is Nernst equation? The relationship between electrode potential and concentration of solution is called Nernst equation. You can write it as E cell or EMF is equals to E naught of cell at standard electrode potential at standard conditions minus 2.303 RT divided by NF log Q. Now what is N? What is F? N is total number of electrons lost or gained by the electrode. 1 F is 96500, F is Faraday, so 1 Faraday is 96500 coulomb. T here is temperature, that is 298 Kelvin. R is gas constant, that is 8.314 joule per Kelvin per mole. And Q is reaction coefficient of overall reaction, which is equals to OS divided by RS. OS is concentration of oxidized state. RS is concentration of reduced state. Okay, so this is the Nernst equation, relation between electrode potential and concentration of the solution. Now at T equals to 298 Kelvin, the Nernst equation become E cell equals to E naught cell minus 0.0591 divided by N log Q. Because we know the R, we have given the 2.303. If we put the T value, we just solved it and it is coming out as 0.0591 divided by N. F is also, we know that is 96500 coulomb, right? So we just solve all these constant values we just solve this term and we have a value that is 0.0591 only if T is 298 Kelvin divided by N log Q. The EMF of a standard cell does not change with the temperature. Okay, so this is important that EMF of a standard cell means not, we are talking about the E naught of cell, does not change with the temperature. Western cell is a common example of standard cell. There is an example given for the standard cell, that is Western cell. Okay, now there are two important applications of Nernst equation. Okay, now we see the applications, Nernst equation and its applications. So first one is to find the equilibrium constant. If we want to find out the equilibrium constant of any reaction, we can use the Nernst equation. How? So at equilibrium, E of cell becomes 0. So therefore, E naught of cell will become equal to 0.0591 divided by N log K. Because it is, the equation was, initial equation was E of cell is equals to E naught of cell minus this term, right? But we have E of cell is 0, so that minus will become positive. So E naught cell will become equal to 0.0591 divided by N log K. Here K is equilibrium constant and thus we can find out the equilibrium constant. Second application is to find the Gibbs free energy change. So del G naught is equals to minus N E naught of cell F. Okay, so you can also find the Gibbs free energy change using the E naught of cell, electromotive cell. Okay, electromotive force of cell. So E naught of cell will come out from the Nernst equation, and here del G naught is standard Gibbs free energy change. Okay, so this is the equation when we use the Nernst equation for finding the Gibbs free energy. Okay, so now let's see the relationship between cell potential and Gibbs energy change, that is del G. So in an electrochemical cell, maximum work done, del G, is given by del G is equals to minus NF times E cell, where F is Faraday's constant, N is number of moles of electrons transferred. A galvanic cell does electrical work by transferring electrical charge through an external circuit. When small amount of current is drawn from the cell, then del G will become equal to work done by the electricity. And for spontaneous reactions, del G is negative. So E cell is positive. Because del G become negative. And we have minus N already here. So E cell should be positive to be the negative value of del G. So for spontaneous reaction, del G is negative and E cell will be positive. Okay. If del G of system is positive, then the process would be possible only if the surrounding do electric work on the system, as in electrolysis. And if del G of the system is negative, then the system does electric work on the surrounding, as in galvanic cells. For a voltaic cell, the work is done on the surroundings, thus given a negative sign, and hence del G is equals to W max, which is equals to minus NF E of cell. Negative sign represents the work is done on the surroundings. And the standard free energy del G naught is given by minus NF E naught of cell. The relation between cell potential E naught of cell, free energy del G naught, and equilibrium constant Kc is given by this equation. That is del G naught is equals to minus 2.303 RT log Kc. Okay, so if we have two of them and we have to find the third one, we can use this equation. Okay, relation between cell potential, free energy, and equilibrium constant. Okay, now del G is equals to minus NF E naught of cell. We know that, right? So we can put it here. So we just put it that E naught cell and E naught cell will become equal to 2.303 RT by NF log Kc. Okay. If two half reactions having potential E1 naught and E2 naught are combined to give a third half reaction having a potential E3 naught, then we can also do this, that del G naught of third reaction is equal to del G naught of first plus del G naught of second. Or you can write the del G is minus NF E naught, so minus N3 F E naught 3 is equals to minus N1 F E naught 1 minus N2 F E naught 2. Or minus we take common from this, so all the terms will become positive. N3 E naught 3 is equals to N1 E naught E1 plus N2 E naught 2. Right, F is common, F is constant, so it will cancel out. And E naught 3 for the third reaction is coming out as N1 E1 naught plus N2 E2 naught divided by the N3. Okay. So let's move on to our next topic, that is batteries. A cell or a battery, arrangement of one or more cells connected in series, okay, you can say this also as a battery, is basically a galvanic cell and used where the chemical energy of redox reaction is converted into the electrical energy. So a galvanic cell is a cell and it is used where chemical energy of redox reaction converting into the electrical energy. Okay, so battery is basically a galvanic cell in which chemical energy convert to electrical energy. And there are two types of batteries. First one is the primary batteries. The battery in which the cell reaction occurs only once and the battery becomes dead after use over a period of time and cannot be reused again. For example, dry cells like Leclanche cell, mercury cell, etc. And hence primary batteries are not rechargeable. Okay, we use the primary batteries once and then we throw out. We can't recharge them and use again. An example are dry cell, mercury cell, etc. Okay. Under the primary cells, we have first category, that is dry cell or Leclanche cell. It is also called primary voltaic cell. The electrode reaction involved in this reaction are in this cell are at anode. This reaction is happening. That is zinc giving us zinc 2 positive plus 2 electron, and at cathode this reaction is happening. MnO2 plus NH4 positive plus electron giving us MnOOH plus NH3, and the cell potential for this cell is 1.6 volt. Okay, and second type under the primary batteries are mercury cell. Mercury cell suitable for low current devices like hearing aids, watches. So we use the mercury cell in all these things. The electrode reactions for the cell are at anode zinc Hg plus 2 OH minus giving us zinc oxide plus H2 plus 2 electron. At cathode HgO plus H2O plus 2 electron giving us Hg plus 2 OH minus, and the overall reaction will be combination of these two reactions going on anode and cathode, that is zinc Hg plus HgO giving us zinc oxide plus Hg in liquid. Okay, so this is the overall reaction happening in the mercury cell, and these are the reactions at anode and cathode respectively. Okay, now let's see the secondary batteries. These are also called reversible or galvanic or voltaic cell. These are rechargeable because on charging reaction become reverse. An example are lead accumulator, lead storage battery, nickel cadmium cell, etc. Under the second batteries, we have first type, that is lead accumulator or lead storage battery. In lead accumulator, the electrons are made of lead and the electrolyte consists of dilute sulfuric acid. The electrodes are usually cast from a lead alloy containing 7 to 12% of antimony. Why? To give increased hardness and corrosion resistance, and a small amount of tin for better casting properties. And the electrodes are coated with paste of lead 2 oxide, that is PbO, and finely divided lead. After insertion into the electrolyte, a forming current is passed through the cell to convert the PbO on the negative plate into sponge of finely divided lead. On the positive plate, whereas the PbO is converted to lead fourth oxide, that is PbO2. So these are the steps that what is happening in the lead accumulator type of battery, lead storage battery. What are the reactions, or what is the process happening on anode? What is the process happening on cathode? Why electrode is made of such a particular amount, type of compound, while cathode is made of particular type of compound. Okay. Now the half cell reactions when the battery is being used up are at anode it is lead plus SO4 2 negative giving us PbSO4 plus 2 electron, and at cathode it will be PbO2 plus SO4 2 negative giving us plus 4H plus 2 electron giving us PbSO4 plus 2H2. And overall reaction will be the sum of these two reactions, that is lead plus PbO2 plus 4H positive plus 2SO4 2 negative giving us twice of PbSO4 plus 2H2. The reaction is reversed during charging as we studied, and during charging the following reaction occur. Each cell gives an EMF of about 2 volt, and in motor vehicles a 12 volt battery of 6 cells is usually used. The lead acid battery produces 80 to 120 kilojoule per gram. Okay. Now fuel cells are another means by which chemical energy may be converted into electrical energy. Okay, so fuel cells are the another means. We have studied so many types of cells till now. So now we are studying about the fuel cells. So they are the another means by which the chemical energy may be converted to the electrical energy. Energy can be obtained indefinitely from a fuel cell as long as outside supply of fuel is maintained. For example, H2O2 fuel cell. This cell was used as a primary source of electrical energy on the moon flights. The overall cell reaction produces water, which is used for drinking by the astronauts. Half cell reactions involved are at anode 2H2 plus 4OH minus giving us 4H2O plus 4 electron. At cathode O2 plus 2H2O plus 4 electron giving us 4OH minus. Overall cell reaction will be 2H2 plus O2 giving us 2H2. The efficiency of fuel cell is ratio of change in Gibbs energy del G to the heat of combustion del H, and mathematically it can be represented by eta is equals to del G by del H times 100. Eta is thermodynamic efficiency of a fuel cell, del G is work done which can be also equal to minus NFE naught of cell, and del H is equals to heat of combustion. Okay, so let's talk about the corrosion and its prevention, and it is important topic to talk about while studying the cells. So corrosion is basically an electrochemical phenomenon. Metal is oxidized by the loss of electrons to the oxygen and form metal oxide. Example, conversion of iron to the rust, Fe2O3.XH2. The tarnishing of silver due to the formation of Ag2S, or development of a green coating on copper and bronze. These all are examples of corrosion happening. So corrosion of iron, known as rusting, occurs in the presence of water and oxygen. Like at anode, it will be 2Fe giving us 2Fe2 positive plus 4 electron. At cathode, O2 plus 4H positive plus 4 electron giving us 2H2. And overall reaction will become equal to this, that is 2Fe plus O2 plus 4H positive giving us 2Fe2 positive plus 2H2. Fe2 positive ions further oxidized by atmospheric oxygen to Fe3 positive and form hydrated ferric oxide Fe2O3.XH2. Okay, so the overall reaction which happened for the corrosion, we get the Fe2 positive, and Fe2 positive further oxidized by atmospheric oxygen, giving us this ferric oxide, hydrated ferric oxide, that is Fe2O3.XH2. So 4 Fe2 positive plus O2 plus 4H2O give us 2 Fe2O3 plus 8H positive. and again some amount of water will add into this Fe2O3 obtained, and it will give us the hydrated ferric oxide, which is rust basically, Fe2O3.xH2. Okay. Now, how can you prevent the rusting of iron? So, rusting of iron can be prevented by the following methods. First one, barrier protection through coating of paints or electroplating, which protects the surface of the iron from the outer hydration or oxygen. Second, galvanization or coating of surface with the tin metal. And third prevention method is by the use of anti-rust solutions, which can't be, allow the corrosion or rusting to happen. Such type of solution are anti-rust solution. So these are some solutions or preventions for the rusting of iron. Okay, so we are at our summary slide, and these are the major concepts which we have covered. A salt bridge is a device in galvanic cells that maintains electrical neutrality by exchanging ions between half cells. The electromotive force EMF of a galvanic cell is the voltage generated when no current flows. The EMF can be calculated using the standard electrode potentials of half reactions. Electrode potential is voltage developed at an electrode in equilibrium with its ions. The electrochemical series is a list of elements by their standard electron potential in order of their ability to be reduced. The Nernst equation relates cell potential to the standard electron potential, temperature, and reactant product concentration. The relationship between cell potential E and Gibbs free energy del G is given by del G is equals to minus NFE. In the standard state, it will become del G naught is equals to minus NFE naught of cell. Batteries convert chemical energy to the electrical energy, and fuel cells convert chemical energy into electrical energy through redox reactions. Corrosion, lastly, is the degradation of metals due to chemical reactions with their environment, often cause rusting of iron and steel. Okay, so these are the major concepts we have covered, we have studied in detail. Okay, thank you.